Hello, Geometry, and welcome to Lesson 5.2 on bisectors in triangles. So, luckily, right, we just did Lesson 5.1, and we talked about two types of bisectors. We talked about a perpendicular bisector, and we talked about an angle bisector. And we learned a couple theorems that we're going to need to know going into this lesson. Well, now we're going to talk about these bisectors, but in triangles. Now, let's recall that we can find the perpendicular bisector of a segment, and we can bisect an angle. Well, in triangles, there are 3 sides and 3 angles. So for these, there's going to be 3 perpendicular bisectors and 3 angle bisectors to talk about in our triangles. So let's see how they behave with each other. All right. So first, the concurrency of perpendicular bisectors. So we're going to focus on the perpendicular bisectors first. So it says that the perpendicular bisectors of the sides of a triangle are concurrent at a point equidistant from the vertices. Equidistant from the vertices. So in this picture here, all right, we have 3 perpendicular bisectors. Those would be PJ, PK, and PL. They make right angles and they break the sides into congruent parts. All right. Therefore, PA is going to equal PB is going to equal PC, which means that those segments are congruent. Now, this word concurrent, right? Concurrent means 3 or more lines that intersect. 3 or more lines that intersect. Of course, if it's just 2 lines or segments, we just say that they intersect. But when you have 3 or more, they are concurrent. And again, this is something special about the perpendicular bisectors in a triangle. Okay. And again, can't emphasize enough this idea of equidistant from the vertices, right? That's very important. Okay, so let's kind of prove this theorem in the next slide. All right. All right, so it says when 3 or more lines intersect at one point, the lines are called concurrent, right? The point where the lines meet or intersect is called the point of concurrency. How do we prove the point of concurrency of the perpendicular bisectors theorem? All right, here we go. So we are given triangle ABC with midpoints J, K, and L and perpendicular bisectors Q, R, and S. So Q, R, and S are lines, okay? And we need to prove that lines Q, R, and S are concurrent at a point that is equidistant from A, B, and C. Well, it's just 3 steps. Here we go. So number 1, we're going to let point P, let P be the intersection point of Q, of line Q, and line R. So here is Q, here is R. Where they meet, let's call that point P. By the perpendicular bisector theorem, we will know that P to A equals P to B, and P to B equals P to C. So I'll say it one more time. By the perpendicular bisector theorem, and again, this is from the last lesson, we know that P to A equals P to B. So P to A, I'll do this here. Let's change colors, blue. So P to A is congruent to P to B. And again, the idea is that, I guess I have to use like 4 lines. 1, 2, 3, 4. 1, 2, 3, 4. Okay? And P to B is equal to P to C. So P to B is equal to P to C. And the idea is the fact that any line on a segment's perpendicular bisector is equidistant from the endpoints of that segment. All right. Well, then we can use the transitive property. So it says therefore, right, PA is equal to PC by the transitive property. And again, as you can see, they're all congruent to each other. Right? Okay, so now the part is like, how do we show that they're concurrent now? Okay, well, step 2, I'll do it right. Let me move my thing out of the way here. Okay, so step 2, so now we're going to say by the converse to the perpendicular bisector theorem, right? So right now we're saying P is the intersection of point Q and R, right? But if PA is equal to PC by that transitive property, then that's saying that P is equidistant from A to C, which means that P also must lie on S, perpendicular bisector S. P must also lie on line S, the perpendicular bisector of segment AC. So now we know that, I'll do it in green, we now know that PS, right? P is on S. So then the third idea I'll put right here. Okay, so that means that P is the point of concurrency of Q, R, and S. And P is equidistant from A, B, and C. And there we go. And we've proved that P is where those 3 perpendicular bisectors meet. Now, this point where these 3 perpendicular bisectors meet has a neat name, and we're going to talk about it right here. Okay, so this again is talking about circumscribed circles and the circumcenter. So it says, how can you construct a circle that contains all 3 vertices of a given triangle? Right. So a circle that contains all 3 vertices of a triangle, which means that all 3 points around the triangle, right, all 3 corners, are on the same circle, right? Well, this would be the idea of making a circle circumscribed about a triangle. So we're going to circumscribe a circle of a triangle. So here's the idea, right? We want to take a circle, and we want to draw it around the triangle so all 3 corners are on the triangle. So corner A, corner B, and corner C. Well, remember that this point is that point of concurrency where the 3 perpendicular bisectors meet. This point is given the name circumcenter. I'll draw it nicer so you can actually read it. Circumcenter. Actually, it's right there too. And I think it's called the circumcenter because it's the center of the circumscribed circle. Circumcenter, yes? And again, the reason we can use this point as the center is because it is equidistant to A, B, and C. So each of these is considered the radius, right? So A to that point, B to that point, C, these are all radii, right? So if you want to put an R for radius. And they're all the same length, okay? So again, it is the circumcenter that is the point of concurrency, and it is the center of the circumscribed circle. Okay? So try to keep that in mind. Now, I'm going to let Savis show you how to do the construction, and then we're going to do it ourselves. Okay, so you can see the different steps right here. And again, we're going to, I'm going to let Savis do this for you as we go to that website, so see this. And then we'll do it by ourselves using Desmos Geometry. Okay? All right, so let's go ahead and go to, there we go. Ooh, fancy. All right, here we go. So, first things first, right? We're going to take a triangle and construct the perpendicular bisector of one side. So there you go, perpendicular bisector. Then we're going to construct a second perpendicular bisector. There we go. Now that we have that, we're going to identify the intersection of those as the circumcenter. There we go. And then fourth and final step, now we're going to use a compass and use the center. The circumcenter is our center. One of the other corners is going to be the length of the radius, and we draw our circle around, just like that. And there we go. So let's actually do this together in Desmos Geometry. I would suggest you do it with me as I do it. So Desmos Geometry. All right, so you can draw a triangle, any kind of triangle you want to. Understand that this triangle is going to go around. Now notice that when I made this triangle, I'll do that again. You have to go back to the first corner to make that triangle stand out. Okay, so first step, we're going to make the perpendicular bisector of one side. Now I'm going to kind of cheat here because this has some tools. So the perpendicular bisector has to go through the midpoint of a side. So I'm going to choose this bottom side. Notice when I click the midpoint button, so more tools midpoint, and I hover over a side, it shows the gray dot. There's the midpoint. And now I'm going to draw us a perpendicular. So again, more tools, perpendicular. It says select the slope. So I want to be perpendicular to this side, and I'm going to go through that point. There we go. So that's my first perpendicular bisector. I'll do the same thing, more tools, midpoint. I'm going to click this side over here, get its midpoint, and again, I'm going to do a perpendicular. So more tools, perpendicular, choose this side as the slope, and there we go. And the point where they intersect right here, I'm going to change my triangle just so you can see this a little bit better. I'm going to make it more acute. The point where they intersect, that's going to be my circumcenter. So this point right here, I'm going to label as my circumcenter. Okay. And now to get the circle, we're going to grab the circle. My center is the circumcenter, and I can pick any point. That one, or this one. And if I connect it, there's my circle. Now, a couple of things to show you real fast. So an acute triangle, the circumcenter is in the inside. Okay, I spelled circumcenter wrong. It was bugging me. I'm sorry. Circumcenter. There we go. Okay. You probably noticed that too. Why didn't you tell me? So in an acute triangle, circumcenter is on the inside. If I try to make this angle a right angle, notice where the circumcenter goes. So if this angle is a right angle, if it's a right triangle, the circumcenter is on the hypotenuse. It's actually the midpoint of the hypotenuse because it's going to be equidistant from these two endpoints on the hypotenuse. And then if you open up even further to make it an obtuse triangle, notice what happens to your circumcenter. It goes on the outside. Okay, and again, that's because the length from the vertices, you know, it has to get longer, so it has to go outside the triangle. And there you go. All right, cool. So that's how you construct a circumscribed circle. All right, so let's do one problem in the notes, and then we'll be done with this video. Okay, here it is. Oh, sorry. Got to go back. There we go. It says use a circumcenter. So it says here, a city manager wants to plan or wants to place a new emergency siren so that it is the same distance from the school, hospital, and recreation center. Where should he place it? Right? So same distance from these 3 points. So I'm going to make the hospital a point. I'm going to make the rec center a point, and I'm going to make the school, right? School, hospital, and rec center, and the school a point. And I'm going to connect them with a triangle as best I can. So this looks like an obtuse angle, maybe close to a right triangle, okay? So now what you need to do is you need to, again, so we created the triangle. So the second thing we're going to do is we're going to create the perpendicular bisectors of two sides. So find two perpendicular bisectors. It doesn't matter what two sides you use. I'm going to choose the hospital to the rec center. So I'm going to mark the midpoint where I think is the midpoint. And now I'm going to go perpendicular. Now I know this is the midpoint because I feel like those two are congruent. And perpendicular will be something like this. There we go. So that's one perpendicular bisector. I'll do the same thing over here to the side between the rec center and the school. I'll pick a midpoint, mark these two congruent, and again, I'll try to go perpendicular. That's not, sorry. There we go. That's the best I can do. It's weird from a right-handed person's perspective. That's supposed to be right angle, okay? And then 3, we're going to mark the point of intersection where the siren should be. So the siren, the emergency siren, should be the point of intersection. Which again will be called the circumcenter. So that would be right here. There's where the siren should go. Right at that dot. And again, like I said, because it looks a little obtuse, just outside the triangle. All right, good. There's the first video for lesson 5.2. Second video is coming up soon.